In physics, the slang term oomph corresponds to the concept of momentum. It does not have a formal long-form name. Momentum is defined as the product of an object's mass and its velocity. It is a vector quantity, meaning it has both magnitude and direction. An object with more oomph, that is, more momentum, is harder to stop. Examples showing how oomph relates to momentum. Mass: a heavy object moving at a certain speed has more momentum than a lighter object moving at the same speed. For example, a large boulder rolling slowly has more oomph than a small pebble rolling at the same speed because of its greater mass.
All right, let's talk about a law of physics. That is so fundamental, it's basically running the show behind everything, from a perfect break on a pool table to launching a rocket clear out of our atmosphere. It's all about the universe's most important rule of, well, let's just call it oomph. So, have you ever thought about this? It sounds kind of weird, right? Totally counterintuitive. But the answer all comes down to one single concept that keeps the physical world in balance. That concept is momentum. And trust me, by the time we're done here, you're gonna get it. Okay, so let's dive right in. Before we can talk about the conservation of momentum, we first have to figure out what momentum actually is. And the simplest way to think about it is as the universe's own measurement of how unstoppable something is. And I absolutely love this description, oomph, because it's something we all just intuitively understand, way before you even think about the math. A feather floating in the air? Super easy to stop. It has basically zero oomph. But a charging rhino? Yeah, that's a whole lot of oomph. You're gonna wanna get out of the way. So here's the official definition, and it's actually beautifully simple. See, momentum isn't just about how heavy something is, and it's not just about how fast it's going. It's the ultimate team-up of both. It's the mass of an object times its velocity. How much stuff is moving, and how fast is it moving? That's really it. And believe it or not, that entire powerful idea boils down to this one elegant little equation, P equals m times v. And this formula is the key that unlocks that whole bullet and bowling ball question. The tiny bullet has a really small m for mass, but a gigantic v for velocity. The bowling ball, it has a huge m, but a pretty small v. And what's the result? They can both pack the exact same punch, the same momentum. Okay, so now that we know what momentum is, we can get to the really cool part, how it leads to one of the most foundational, absolutely unbreakable laws in all of physics. And I'm not kidding. This isn't just a suggestion. It's a rule that as far as we've ever seen, the universe never breaks. Now there is one little condition. For this law to really work its magic, we have to talk about something called a closed system. Just think of it like a self-contained bubble. Nothing from the outside, no friction, no air resistance, nothing can get in to mess with what's happening on the inside. It's like the perfect, clean laboratory for physics. And here is the law itself. So simple, but so profound. What it's saying is that inside that bubble, you can't create momentum out of thin air, and you can't make it disappear either. It can get passed around, sure, transferred from one object to another, but the grand total, the total amount of oomph in that system will always, always be the same. Let's make this real. Imagine two billiard balls on a table. Before they hit, let's just say their combined momentum is 10 units. Then, bam, they collide. They bounce off, changing their speeds and directions. But here's the magic. If you were to measure their total momentum after that collision, you'd find it's still exactly 10 units. The oomph wasn't lost, it was just perfectly redistributed between the two balls. So the big takeaway is that momentum is always conserved in one of these closed systems. But that probably brings up a question for you. If the law is always the same, why do collisions in the real world look so different from each other? Yeah, exactly. Think about the difference between two billiard balls smacking into each other versus, two lumps of clay. One goes clack, and they bounce apart perfectly. The other goes splat, and they just stick together. They're totally different outcomes. So what gives? Well, it turns out there are two main flavors of collision. On one side, you have elastic collisions. That's your billiard balls. They bounce cleanly, and in those cases, both the momentum and the energy of motion, called kinetic energy, are conserved. But then you have inelastic collisions. Think of a car crash. The objects get all bent up and deformed. Now here's the key. The momentum is still conserved, but some of that kinetic energy gets lost. It gets turned into other things like heat and sound. Okay, now this is where things get really, really cool. This simple law isn't just about things crashing into each other, it's also about how things push away from each other. And honestly, it is the very principle that lets us leave this planet. And it's probably no surprise that this all connects back to one of the most famous ideas in the history of science, from Sir Isaac Newton himself. You see, his famous third law of motion, it's really just another way of looking at the conservation of momentum. We've all heard this a million times, right? But what does it actually mean? Well, it means that if you push on something, it pushes back on you with the exact same force. And in the language of momentum, it means the momentum you give to an object is perfectly balanced by an equal, opposite momentum given right back to you. And once you start looking for it, you see these action-reaction pairs everywhere. A rocket pushes super hot gas down with a ton of momentum, so the universe demands balance. The rocket must gain an equal amount of momentum upward. A cannon fires a cannonball forward, and the cannon itself gets kicked backward. The universe is just balancing the momentum books. So why does any of this matter to you? I mean, this isn't just some abstract idea for physicists in a lab. Understanding and being able to manipulate momentum is absolutely critical for our technology, our safety, pretty much our entire understanding of the world. I mean, just think about it. Engineers designed the crumple zones in your car specifically to manage how momentum changes in a crash, making it way less violent for you inside. In sports, hitting a home run is all about the perfect, efficient transfer of momentum from a bat to a ball. And astronomers use this very same law to track the incredible dance of planets, stars, and entire galaxies. It really is everywhere. And that brings us to one last kind of mind-bending thought to leave you with. If the entire universe is basically the ultimate closed system, and if this law really is unbreakable, then couldn't that mean that the total amount of oomph created at the Big Bang is the exact same amount of oomph that exists right now? That it's all just been passed around between stars and planets and us for almost 14 billion years? Now that is something to think about. Thanks for joining me on this one.